and now for something completely different, namely game theory. So we're going to look at the Parliament of Micronesia, and in this fine nation, confederation, you have a total member of 14 members of parliament, and it just so happens that they are split up into 4 political parties, A, B, C, and D, which have 6, 3, 3, and 2 representatives respectively. Actually, the real Parliament of Micronesia has 14 members, but they are non-partisan. But let's for the moment assume that they actually form parties, maybe according to the islands where they're from, and they are to vote on whether to pass $1 million spending bill and how this money should be controlled, for instance, to go to the various islands. Majority vote, that is a minimum of 8 votes, is required in order to pass any legislation, and if the bill doesn't pass, well, then nobody gets anything. So it's very clear that the winning coalitions are if A teams up with anyone else, because that gets them to 8 or 9 votes respectively, so that's the majority. Furthermore, if the 3 minority parties team up, they also get to 8, so they also get to pass the bill. And so there's some payoff function V of S for the set S, where S contains, who the members are. Okay, so no, don't worry, this is not the wrong channel, it's still machine learning. The point is, well, we care about this because go and replace the parties with features and replace the payoff by influence, and you actually happen to have a good mechanism for finding out whether a certain feature has, value and what should be attributed to it. But it's just so much easier to think about, bickering politicians than it is to think about feature selection. And so let's, for the moment, stick with the Micronesian parliament. So there are a couple of axioms that you want to enforce. One is symmetry. And that means that for any payoff function V of S not containing I or J, if I add I to it, or if I add J to it, if the value is always the same, then we should also assign the same reward to it. And that already gets us to some rather nice implications, because we know that parties, so remember we have one majority party A and we have 3 minority parties B, C, and D, and we know that if A teams up with any one of them, then things work out okay. So they're entirely interchangeable. Furthermore, if 2 of them team up together and the third one's added, then that correspondingly adds things. And if it's only 2, then 1, then joining doesn't really make a difference. In other words, whether it's B, C, or D being added to a set doesn't really matter. You always get the same outcome. And from that, we can immediately infer that phi of B equals phi of C equals phi of D. And that's a curious result, because remember, B and C have 3 votes, D has 2 votes, and nonetheless, they end up getting the same reward. Now, this isn't too surprising if you look at countries that have coalition governments. In many cases, the minority parties, if you have, one larger party and several smaller parties, even though one party is larger than the other one, they tend to get more or less, the same share of influence. And this is really just game theory in action. The other thing is what you want for a meaningful payoff function, that a dummy player gets exactly the payoff that he or she contributes. So what happens is basically that, if a dummy player contributes exactly, its own value, and that regardless of the original set S, then that dummy player should get exactly the reward of what he or she contributes. Okay, so that's sane. Furthermore, we want additivity. So for any payoff function, the rewards should also be additive. And in other words, phi of I is phi 1 of I plus phi 2 of I. That is a super useful criterion, because otherwise I could easily engineer pathological situations where I take a payoff and split it into partial payoffs or add payoffs together, and I would get some, very strange values. So for instance, I could take a payoff and halve it in two parts and, rescale some in some funny ways, or maybe halve it for some values and not halve it for others. And you will get a weird result. So we really want that additivity. And the nice thing is that the Shapley value theorem tells us that any payoff function that satisfies symmetry, dummy, and additivity that divides the payoff of the grand coalition is uniquely defined by the Shapley value of the game. So that means there's a computational tool now that allows me to decide, how much every participant in that game should get, and there's only one possible choice. So usually theorists love that kind of uniqueness results because it allows them to define in meaningful ways what should happen. And the Shapley value function itself is, well, a slightly intimidating beast, but let me decode it for you. So this term here is the difference if, element I is being added to the set versus if it's not there. And I'm taking the sum over all possible sets that don't contain I. Well, why that don't contain I? Because, well, if it was included, then, that would be kind of pointless. And I would actually get a difference of 0. So technically speaking, I wouldn't have to exclude it, but since the term then is vacuous, well, I might as well. Okay. The other thing is it divides by the cardinalities of the set S. Well, n sounds a little, so n is, the total number. So in the case of the Micronesian Parliament, it would be, n would be A, B, C, D. But you can clearly see that S can range from the empty set all the way up to S being, the set, in this case, n without element I. Okay, so that's why we get n. Then furthermore, this is a combinatorial coefficient that just tells us, well, it's, n choose S. So basically, I take the subset elements from it and I uniformly weigh over all possible subsets, which is also a sane condition. And so that means that we're looking at all the incremental contributions that I may contribute to V, and then I decide that the payoff is just the average over all the incremental contributions, where the average is taken suitably according to cardinalities and, the uniformly over cardinalities, and then within each cardinality, uniformly over all possible choices. Okay? And so it's actually quite easy to check that this satisfies the axioms. Okay, let's look at the first one. That's probably the hardest one to check, namely the interchangeability between I and J. And it's clear that, if this term here happens to be the same whether I use I or whether I use J, then I will get the same algebraic expression. So therefore, that holds. Now the dummy property also holds, because in this case, V of S union I versus V of S is always exactly, V of I plus V of S. And if that happens, well, then I'm just adding and subtracting this, so I just, get V of I, and taking the average over that gives me just V of I. So the dummy property holds, and the additivity is trivial because this is just a linear function of V, so therefore linearity preserves additivity. Okay. Proving that this is the only possible choice is quite a bit more work, but since this is not a game theory class, we can skip it for now. So back to Micronesia. So we have set parties A, B, C, and D, and individually they get nothing. Any coalition, including A, succeeds. The only coalition without A is B, C, D. And so we already knew that the payoffs for B, C, and D have to be the same. And if you work the algebra, you'll get that the payoff for A is going to be 1/2, and the remainder is split between B, C, and D. Okay. Now, in order to get back to feature scoring, that's fairly straightforward. Namely, we just use exactly that feature scoring approach to figure out what the influence of feature I is. So this gets us to what I would call the axiomatic approaches to feature analysis. So let's quickly look at what we want. So the first thing that we want is we want to get some explanation model to explain f, but that explanation model is one that needs to apply locally at, around x. So therefore, that local explanation model gx, so x is where it needs to explain, evaluated x prime should be essentially, phi transpose x prime plus, phi naught, and this needs to match f for x equals x prime. Furthermore, what I want is that if, a feature isn't there, then it shouldn't have any influence. Okay, that's also sane. And lastly, you want consistency. So consistency just means that if, I have, rather than some function f, I have some function f prime, and f prime happens to be designed in such a way that the contribution from I is always larger than the contribution on f, then the explanation for f prime with regard to I should also be bigger. Right? That's, I think, a sane requirement. So if you impose those three, namely local accuracy, missingness, and consistency, then the only feature score that satisfies this is the Shapley value. Now, this is great news because we just now put up some conditions. We proved that under those conditions, there's exactly one feature explainer. Okay, bingo, we can go home. So this, one would hope, would put the problem to rest, right? So after all, the SHAP theorem, solves things. So we should not have any more, feature explanation papers after 2017. Well, we all know that this is not true, but instead there's actually been quite a steady stream of feature explanation tools, and we'll see shortly why that's the case. So just, to look at the good news, well, for linear functions, Shapley value just gives us the original function and the coefficients, and for Lime it gives us the local weightings, and linear model explainers can be seen as special cases. Now, there's, again, the weighting for the SHAP theorem, and this also tells us how we should go and weigh the difference between contributions, because essentially what's happening is that we walk down this dependency tree. So let's say we have, y x1, x2, and then, we get some other function f3, which depends, on x. That's now based on a combination. So therefore, what happens is that as features are combined, so therefore also their corresponding terms need to be combined. And the nice thing is that the SHAP theorem tells us how to weigh terms for Lime. Okay, so remember, in Lime, we said, okay, well, we want to pick some local neighborhood of the observations, and that will help us, weigh terms accordingly, in terms of, mutual contributions. And the Shapley kernel, so the Shapley weighting, actually gives us one of those, and it turns out that this gives us more meaningful and representative features than what you get from Lime, even in the Lime context. Okay, this is a really complicated way of saying you can hack the weights of Lime in such a way that you get the Shapley value and vice versa. Okay. So basically the SHAP theorem, as I mentioned, is that the only score satisfying, those requirements of missingness, local accuracy, and consistency is the Shapley value. But there are a couple of problems. So if you squint hard, actually you don't have to squint that much, but you basically see these terms here, x subscript s and x subscript s union I. So this is basically f evaluated for, the features. Let's say this is my feature vector, and this is maybe s, and this is something else. But the question is, what do I put here? right? I cannot possibly go and just retrain the model. I need to, complete my vector somehow. So one choice would be, for instance, to plug in the mean. The other one would be to draw, these terms, conditioned on what I observe. So this is x subscript s, and this is x, in without s. And this should ring a bell, because before that we discussed exactly what happens with, marginal and conditional distributions. And this is exactly what the motivation of that paper by Janzing et al. Was, namely to find out, how we should fill in the terms. Turns out, basically, just, draw them independently, and that's okay. Now, in short, there's some clever sampling going on. Now, the second part is, well, this is an algorithm that requires an exponential number of calculations, because you need to look at, the power set of n, and that's of size, 2 to the n. So this is not a very efficient way to evaluate the some brute force. And yes, you can do some work on how to parallelize that on a cluster of machines, but I think using math is a little bit better. Okay. Just before we get into this, some more details. So basically what they did is they looked at, feature importance, and they looked at the, overall, terms from Lime. It turns out that if you, use the Shapley value, you get some terms that are a little bit more accurate. And if you use Shapley sampling, it's not too bad either. Basically, you get estimates that are reasonably close. And my guess is if they, used more sampling, that would have been better. But what you can clearly see is that, the law of large numbers makes those gaps smaller as we sample more. Okay. Now, the same thing holds for a sparse model. They didn't really explain very much exactly what we're supposed to see, but suffice it to say, sampling the Shapley value, if you sample enough, gives you something that's sensible. Now, there are a lot of really clever, fast approximations that people, used, and the reason is simply, well, because the original thing is, an exponential algorithm. So, for instance, there's something called fast tree SHAP. And it turns out that for a decision tree, Shapley values are easier to compute, because all the decisions are happening locally anyway in some leaf. So therefore, you can avoid having to reevaluate all the terms independently. And for many differences, basically nothing changes. So let's say I sit on a terminal node. I haven't used some feature, let's say feature 3. Then I can immediately, drop out all the features that weren't even used in the past. And if not, then I basically can end up, picking random paths and doing some clever pre-computation and all of that. So the other thing is I can just go and only compute, the first k terms, and that reduces the computational cost from 2 to the n. Okay, so that's clearly a typo, right? So it's 2 to the n to n to the k. Well, that's still expensive, but you've now made an algorithm that was horrible and exponential first to one that's horrible and polynomial. So we won a little bit. Sampling terms also helps. So basically, you can actually go and combine both things, where you have an approximate expansion, and maybe the first few terms you compute exactly, and the rest you sample. So there are lots of papers that you can write. But you could basically sample first, you pick a cardinality, and then within the cardinality, you pick a random element from the set. Then for deep learning, there's something called deep SHAP, which also uses a number of approximations. But basically, this Shapley paper has led to a plethora of other feature selection papers that try to do approximately what is really prohibitively expensive otherwise. Fortunately, the two authors that wrote SHAP, actually, so Lundberg specifically, he put his code up on GitHub, and so now we don't really have to suffer anymore from worrying about whether it works or not, but that's okay. So this gets us back to the issue of reference scores, namely what should we do with left out features. In general, well, don't try to model a conditional distribution. A lot of papers try to do that first for Shapley values until, well, Dominic basically and the team wrote the paper, which showed that, well, this is actually not improving things, but making it worse. So draw unrelated values for the features that we're leaving out. This is a little bit more tricky for tabular and text data, because if I have, you know, for instance, the dog, and this is now the part of the text that I want to retain, then I can clearly not just, you know, plug in arbitrary, you know, terms here. So for instance, I cannot say the dog watermelon. That's probably a terrible idea, because, well, dogs and watermelons are fairly unrelated. At least I hope you don't have a dog that you decided to call watermelon, but short of that, it makes no sense. Basically, in this case, you may have to do some degree of conditional sampling, but yeah, for text and images, this is still very much ongoing research. So here's a nice toy example from the Janzing et al. Paper, and I'm not going to walk you through detail, but basically what turns out to be the case is, so they construct some simple toy function f, and this toy function f only depends on x1, right? That's the important thing. So therefore, what you would expect is that, you know, phi2 has to be 0 because it doesn't depend on x2, and phi1 is, you know, something, it might be 1, for instance. Furthermore, they construct a joint distribution where, let's say, you know, the values, you know, 0 and 1, 0 and 1, that basically both 0 and both 1 occur with probability 1/2, and the rest is all 0. And that is essentially something where you could easily design a graphical model with a hidden confounder, right? So I have basically this model. This is x1, this is x2, this is some variable hidden, and basically I first go and, you know, roll the dice and decide whether it's going to be 0 and 1, and then, you know, x1 and x2 just copy that value. In any case, if you do that and you work through the algebra, then you will find out that if I take conditional expectations, then phi2 is not going to be 0. And if I take the marginal expectations, then phi2 vanishes. And so this gives, I think, a good explanation and credence to the fact that, at least in a situation where you have that kind of conditional independence, well, you should go and sample accordingly. And that also explains why it's maybe not perfect for text, because you don't have conditional independence of words given some latent term, because you also have lateral dependence between them. So remember the working out athletes versus running example. In this case, you do get dependence, so therefore that model doesn't work so easily anymore. Okay. Now, besides Shapley values, there's another approach that you could take. And this is, at first glance, you know, quite alien. So basically the axioms are as follows: that if I want to have an explanation, so phi of I and at the location x, then the sum of the explanations over the features should explain the difference between f of x and some reference value f of x naught. Okay, that's sensible. You also want to have sensitivity, so that's the same thing as before. If it doesn't depend on I, then okay, drop it out. Lastly, you want to make sure that the actual scores don't depend on how the function is implemented. Again, that's very, very sane, right? Same thing as before. Also linearity in the scores, and then furthermore symmetry. So The requirements look very, very similar to what we had for Shapley. Now, you might wonder, why on earth are we even discussing a second set of such axioms? Well, because the Shapley terms only really made any sense for a situation where we have basically zeros and ones, but a lot of inputs are actually scalar, and so therefore I will need a slightly different set of statistical tools to deal with scalars. The good thing is there's a nice result by Sundararajan and Najmi from 2 years ago, and it basically says that phi I of x needs to be computed as an integrated gradient, and so here we have the difference between x and its reference value, and there we have an integral over a path integral. So this is basically the derivative with regard to coordinate xi, and then integrated again over alpha. And it turns out that only this situation, the setting, explains terms. So you're basically looking at an integral from a reference term to x prime along various directions, and you're adding up the influences along those various directions, and that's what gives us the overall influence. So this works rather nicely for a deep network, and you may actually be able to compute that more rapidly than the exponential term, because now it's linear in the coordinates, and then it depends obviously also on how accurately you want to approximate this integral. So they can just use numerical quadrature for that. That's actually quite nice. So furthermore, this turns out to give us a nice way of getting at the Shapley values by using the integrated gradients. If you want to know more about that, again, look up the excellent paper by Dominic Janzing from last year. And that also discusses that connection quite well.